Now, good afternoon. We started in the morning, but I'm afraid I'm giving another confusion because my topic is about engineering, not biology. The scale-wise, it is very small scale compared to the previous presentation. But anyway, I determined to present this one because I thought this is the one I can, actually present. Maybe you are interested in. So this work's done by my students here, Woo, Kim, Han, Jung, and I. And then Professor Yoon also gives some good advice and effort to this topic. And I would like to talk about inspiration. For 2 years ago, our colleagues, including me, went to the Totori in Japan. As you see here, and then there is some very nice sand dune. At that time, this guy asked me, can you calculate drag coefficients of artificial reefs? And then I told him, who cares artificial reefs? Then he mentioned about we need to know the drag coefficients because when we install artificial reefs on the seabed, there are many hydrodynamic forces. So it is very important to know drag coefficients to calculate sliding and overturning, those things. At that time, I used to calculate drag coefficients of anchors in design of tunnel structures used for protecting submarine power cables, using some numerical schemes here. And they put the anchors and then some inlet and outlet. So we did calculation. So yes, I can do that if you give me some information. And he gave me, and then I calculated CD, which is the drag coefficients as shown here. And I would like to characterize using some dimensionless characteristics. And then I thought, it is very interesting about artificial reefs. So I investigated artificial reefs a little bit, and then what I can do, I think about that, and I can do that flow analysis. And then probably wake collision is most important, one of the most important things. And then I extended my research topic to placement models for last 2 years. That's the main story. And this is the contents of this presentation. And now we introduce marine ranch project in South Korea. There are two types. The first one is pilot project. The second one is practice. So basically, pilot marine ranch project governed by government. So we constructed 5 sites here, and then many sites for practice. This marine ranch project, usually we are using artificial reefs. So I investigated what artificial is about, and then basically many scientists say current carry nutrients and organic matters around artificial, especially downstream. And then planktonic larva, is that right, larva? Yeah, follow, and fish follow, those mechanisms. Of course, there is some debate about artificial reefs. Some scientists say attraction is the only possible way. Some scientists say no, production is another option. That is called attraction and production debate about artificial reefs. But I'm engineer, so I believe artificial reefs good. That's a big assumption. And then I also realized in traditional way, the artificial reefs are very small size. So stacking way, we are attracting the marine species. Nowadays, the size is very big. The material is very diverse, steel, reinforced concrete, composite, etc. So the structural behavior, because the frame and steel frame and those things are connected by weld. So there is some structural issue, I guess. So we did continue the research. And there are 3 types of artificial reef in South Korea. The first one is called general artificial reefs. This is nothing but approved by Central Artificial Reef Committee. So since 1971, we have 1 general artificial reefs. And then the other one, the test and research artificial reefs are all pattern developed by individual or government or supervisions for research and development purpose. So these are candidates to be general artificial reefs. So I'm showing here some of the 72 general artificial reefs, and this artifice can be classified box type, tunnel type. This is my classification. Yeah. And then I investigated the problems, no data for drag coefficients, no comparison for structural responses, no consideration for wake regions, no design guideline in detail, of course, no practice. So I tried to solve these things. Today I will introduce wake regions. For the analysis, I made some hypotheses here. The water is incompressible, viscous, and Newtonian flow. And isothermal flows exist in the water, and then the flow is steady. And the governing equation, of course, Navier-Stokes equation, and etc. And then the numerical schemes, element-based finite volume method we used. And in the modeling process, we constructed profile like this way. So in front face, we put the inlet velocity. And at the back side, we put the outlet. And then bottom, we assume smooth wall, no friction. And then we apply three surfaces as a symmetric planes. Before calculating the characteristics, we calibrated our flow analysis schemes. So this the horizontal axis is the CD values from reference, and these are our CD value from our study. So we compare together, and then the tolerance is within 10%. So we thought our numeric scheme is pretty reasonable. And then I'm introducing here wake region. So wake region is very important because at that region, the marine biospecies saving energy. So that means here main current comes from the front, and then there is artificial reef. Then in that area, wake region, the water speed is very less than the other side. So marine species usually stay here, and then this wake region provides shelter, feeding ground, spawning ground, rest area, or temporary stopover for marine bioresources. That's the region is called wake region. The problem is, long time ago, Japanese scientists proposed wake length concept. So if we calculated this wake length, then we may estimate the wake region. But as you see, there are many wake lengths because there are many wake planes. So we needed to provide more quantitative way to measure the wake region. So, as I mentioned here, Professor Sawaragi and other people proposed wake lengths to quantitatively represent the wake region. However, in theory, there are plane 1, plane 2, there are many planes. So there are many wake lengths can be. So this slide shows the wake region profile. The first one is box type, and the second is modified box type. So these are all constructed by reinforced concrete structures. But the difference between these two, the first one has steel box inside. The second one does not have the steel box inside. Then this one showing the front view, plan view, and side view. And then you can see the wake region are very similar, but you can also observe some difference. So this one shows some animation, what's the difference between. And then you see here, the steel box side there is some recirculating water flow inside. But here, you cannot see that. That's the main difference. And then we calculate the wake length for 24 general artificial reefs. So depending on the type, the wake lengths are pretty different. For example, AR-19 has about 16 meters, but some does not have at all. All right? But compared to their, the height, so this red line shows the efficiency. So usually height means the size of the artificial reef. So compare with respect to the height, we calculated the wake length. Then this one has the largest wake length, but with respect to their height, the efficiency is not very good. We can see that. And then to overcome the shock, the disadvantage of wake length, we try to capture wake volume instead of length, instead of the area. We try to capture wake volume. How to do? So we use the element-based finite volume method. That method is very good for measuring the finite volume which has recirculating water velocity. So we combine together, so we calculate the whole region of wake region. That's the basic idea. So this is the first one, box type. And then we investigated wake volume. And then this is showing Reynolds number and flow velocity relationship. And then this one shows wake volumes according to inlet velocity. So we change the inlet velocity and then we investigate what the difference. But there is no variation at all. And then also we try to see the effect of the orientation, flow direction, And then, as you see, with respect to flow directions, wake volumes are fluctuated. Then we did several analyses with different artificial reefs. So we found wake volume is independent of inlet velocity here also. And then we investigate the relations between wake volume and AR height. Then you can see that if the size is increased, the wake volume increases. That's the basic result. And then in this case, this artificially, when we calculate, there is no wake region. No wake volume. But if we put some plate here in front of the face, and if we put some boulder inside, then we can make wake region. So that's we investigated. And then the last one is placed model. So this is the rank of the geometry. So say this is an AR module, then multiple AR module can be AR set. The multiple AR set can be AR group, and then multiple AR group can be AR complex, those things. So usually we install many artificial reefs in that area, not single one. So this is the classification. Then we investigated the artificial images by multi-beam echo sound in Busan coastal areas. So you see that multi-beam images. So we found there are two types basically. The first one is intensively stacked placement model. So we stacked the artificial reef. And then the second one is flatly distributed placement model. So in the plane, we distributed the artificial reefs. Then we read some paper about urban street canyon. So the pollution, the marine, not marine, the environment scientists, they are used to say the street between the building, they are calling street canyon. So we thought maybe we can call this leaf canyon. So we made that terminology. And then we made two models. The first one is just this way, and then we control the longitudinal interval and transport interval. And the second model is the zigzag style, and then we also control D1 and D2. And then we investigated the wake volumes. So the first case we construct 25 sub-cases, something like this way. And then we found this result. The best way is we reduced the transverse interval, but we increased the longitudinal interval. The best way is D1 is 4 meters. So the original module, the size 2 by 2 by 2. So the 4 meters means double of the lip size. Yeah. Then we can make it good, the wake volume here. And then this one shows the flow velocity at the plane at the 0.5 h, which is 0.1 meter above the sea bottom, as you see. And then these 4 cases, this yellow shows the wake volume, wake region. So in this way, we can calculate, we can imagine how the wake regions are. And this one also shows some animation, how the water flow comes through the set. And as you see in this case, if the transverse interval is too big, then just the water passes by. So it doesn't help the wake region. Yeah, we can see that. Let's go. Yeah. And then zigzag style, also we calculated the wake volume and then compared to others, which one is better, we investigated. And then this one is also show the animation. So if we put the artificial lip in the zigzag patterns, it doesn't work. It takes time, right? Yeah. No animation. Let's move on. Yeah. And then the other cases, we investigated the other 4 cases, and then we made some index. So this one is called unit propagation index of wake volume. So even though wake volume is very large, so here WVM is the wake volume of a single module. And then WVS is wake volume in a set, of the set. And the N is the number of artificial lips. So with this concept, we made some unit propagation index. So if this index is very big, then it is very efficient for the replacement model. That's the basic idea. So among these 4, this one is 1.35. So this is the better one compared to others. And then the other model is intensively stacked placement model. In this way, this is AR1, 2 by 2 by 2, and then we stacked 100 AR1 in 6 different ways. And then this is very ideal model compared to these 3. And then we named hexa, rect, pira, tri, tetra, penta, etc. And then we calculated wake volume, propagation index, and unit propagation index, etc. So we found tetra is the best one amongst the 6. And then we also investigate effect of uniform settlement. So in somehow the artificial lip settled down on the sea bottom. Then as you see, this portion is going to in the seabed. In that case, what happened in the unit volume, I mean the wake volume? That's our idea. So we intentionally show the uniform settlement 20%, 40%, then which means usable volume loss 160 cubic meter, 320 cubic meter, etc. And then we calculate wake volume, and then we compare. So we found when the loss is 20%, then how the wake volume is decreased, and then when the loss is 40%, then how it decreased. Then initially when we decreased 20%, the wake volume rapidly decreased, especially this red one, and then but 40%, and then the decrease is little, small. So because I did this research for last 2 years, I think no conclusion yet. Yeah. But I would like to discuss something. So here the wake region, wake length, wake volume, and AR placement models are discussed. And then wake volume is better than the wake length to quantitatively estimate wake region, of course. No effect of inlet velocity on wake region, but other parameters such as orientation, height have strong effect on wake region. And the water blocking mechanism is important for wake region generation. For example, it is necessary to provide steel plate or stones to invoke wake region. So this is my discussion. And then I mean, I appreciate the Dean, Professor Kim, because he supported me to be here. And I appreciate Professor Chen, because he visited our university. You should come here. And then also, I appreciate Miss Carolina Marin. Do you know her? Yeah? Yeah. She's #1 in single women's badminton now. Yeah. It's amazing, you know. Chinese ladies very strong. Yeah, they're aim about last 20 decade. I'm not 20, 2 decade. They are #1, but now the Spanish lady called Carolina Marin is #1. Yeah. Thank you so much. Yeah. Artificial reefs on the seabed, there are many hydrodynamic forces. So it is very important to know drag coefficients to calculate sliding and overturning, those things. At that time, I used to calculate drag coefficients of anchors in design of tunnel structures used for protecting submarine power cables, using some numerical schemes here. And they put the anchors and then some inlet and outlet. So we did calculation. So yes, I can do that if you give me some information. And he gave me, and then I calculated CD, which is the drag coefficients as shown here. And I would like to, and then Professor Yoon also gives some good advice and effort to this topic. And I would like to talk about inspiration. I mean, for 2 years ago, our colleagues, including me, went to the Totori in Japan. As you see here, and then there is some very nice sand dune. At that time, this guy asked me, can you calculate drag coefficients of artificial reefs? And then I told him, who cares artificial reefs? Then he mentioned about we need to know the drag coefficients, because when we install Now, good afternoon. We started in the morning, but I'm afraid I'm giving another confusion because my topic is about engineering, not biology. The scale-wise, it is very small scale compared to the previous presentation. But anyway, I determined to present this one because I thought this is the one I can, actually present. Maybe you are interested in. So this work's done by my students here, Woo, Kim, Han, Jung, and I, is practice. So basically, pilot marine launch project governed by government. So we constructed 5 sites here, and then many sites for practice. This marine launch project, usually we are using artificial reefs. So I investigated what artificial is about, and then basically many scientists say current carry nutrients and organic matters around artificial, especially downstream. And then planktonic larva, is that right, larva? Yeah, follow, and fish follow those mechanisms. Of course, there is some debate about artificial reefs, characterized using some dimensionless characteristics. And then I thought, it is very interesting about artificial reefs. So I investigated artificial reefs a little bit, and then what I can do, I think about that, and I can do the flow analysis, and then probably wake collision is most important, one of the most important things. And then I extended my research topic to placement models for last 2 years. That's the main story, and this is the content of this presentation. And now we introduce marine launch project in South Korea. There are 2 types. The first one is pilot project. The second one